So welcome back to my channel, and I'm really sorry that I wasn't able to upload the videos. I mean, probably a month, and now I'm back to my college, and I hope that I will able to upload a video in a week. So it's lecture 2 and video number 3. So before moving forward, I just want to recall for a few things. One is that we discuss what is a modular group and how it can be generated by two elements, and we see earlier that it is generated by a finite order element S and an infinite order element T. And then we also shows that both elements can be finite order. So here one order is again finite, S has order 4 and ST has order 6. Now then we further did some problems, and then we define what we call congruent subgroup of level n. The principal congruent subgroup of level n is defined to be as gamma, denoted as gamma n, defined to be as like this. And then we ended the video with a question which actually tells that we can define a surjective homomorphism from the modular group SL to Z to SL to Z mod NZ. And I mentioned last time also that this surjective homomorphism, how it is constructed, is really important for the upcoming results, because in this book which I am following, Professor Ramamurthy books, actually write results in terms of the problems. So yeah, so today we are going to discuss we are going to actually start the video again with a problem which can be stated as a result also, but I won't write it. I just make a star and state the problem that prove that for n belongs to natural number, gamma n is the normal subgroup of SL to Z. And then we also want to say that the index of the subgroup gamma n is finite, and later we will actually calculate the exact order of the gamma n, the index of the gamma n. Now I don't know how you guys actually view this problem, but maybe many of students also see this kind of problems which I'm going to say, that whenever we encounter with showing that the subgroup is normal, for me I actually try to assume or try to imagine a good group homomorphism whose kernel is that subgroup. So if we want to show that gamma n is a normal subgroup SL to Z, I want a good homomorphism from SL to Z to a subgroup, to another group whose kernel is gamma n, because I know that the kernel of a group homomorphism is a normal subgroup, and then actually we are done. And if you observe, the group homomorphism that I want is actually written over here. So if we say define this exact group homomorphism from SL to Z to SL to Z and Z mod NZ, we will see that the kernel of phi is actually gamma n. It's not that hard, just a line of writing and then you will get this result. Not even a result, but an observation. So first part is done because of this nice good looking good looking group homomorphism. And because the homomorphism that we define here is surjective, we showed that it's subjective. I actually gave a hint in the last video. Yeah. So because it's subjective, so we can use the isomorphism theorem and directly state that SL2Z mod kernel of phi is actually gamma n is, sorry, I just skipped one step. Okay. Is isomorphic to SL2Z is equal to image of phi. And image of, because it's subjective, the image is full, the group we are mapping it to. And so I will just move this part. It's now done actually, because what we want is that we want to find the index of the gamma n, and which is equal to finding the cardinality of this group. And because the isomorphism is defined above, actually we are just finding the number of cosets of the gamma n, and because the isomorphism that defined over here, we just say that the cardinality is equal to saying of SL2Z by NZ. Yeah. And now it's not that difficult to actually observe that the cardinality of this group is actually finite, and we are done, because there are only finitely many elements in this part over here. So the modulo n classes, so 2 by 2 matrices whose determinant is 1, and A, B, C, D such that determinant is 1, and A, B, C, D are belonging to Z mod NZ, which is a finite. You can say the ring or a group. Yeah. So if you are interesting numbers, then you will find the interesting part over here. It's actually 1729. And see, any matrices by 2 by 2 matrices, we actually showed that it is generated by the 2 element SMT. So that's only we are doing over here. ST and T some powers, and we are getting a matrix whose entries have such a cool number, 1729. Actually, it's a good question. So it states, I will just show the screenshot. For a prime P, show that SL2Z and PZ is a normal subgroup of GL2 Z times PZ, Z mod PZ. Yeah. And the index of this normal subgroup is P minus 1, and the order of this, and it states further that you need to find the order of the group SL2Z mod NZ. Let me just check it once. There is a slightly correction in the LaTeX note. So it's actually want to show that the order of group SL2 ZPZ is actually PP square minus 1. So again, you see the common part in all these problems is that we are just dealing with some kind of normal subgroup. And again, I will just suggest that you should think of a good group homomorphism from this group to this kind of thing. Am I right? No. I mean, good group homomorphism from this group to some another group whose kernel is actually this group. Yeah. So if you think of such, if you able to think such a good homomorphism, then it's good. But yeah, if not, then you just learn from how can you actually define it. It's not that easy to actually work from this philosophy. There can be some instances where you aren't able to find such good homomorphism, but generally it will work in some kind of standard problems. So from this group, you will define a group homomorphism to another group Z mod PZ star multiplicative group, and the map is sending the matrix to the determinant of the matrix. And again, it's not that difficult that for every p element there exists a matrix such that, I mean, for every element in this multiplicative group there exists a matrix whose determinant is actually that p naught. Yeah. So again, this map is surjective, not that difficult to observe, and rest is just calculation, and just not that much calculation, just using a isomorphism theorem, and then we are done with this problem. That's showing that firstly that we actually able to show that the kernel of this group homomorphism is SL2Z mod PZ, and next part is using the isomorphism theorem to conclude that the group GL2, it's my first time that recording videos on iPad, so I'm really sorry for this. And for this iPad, I just really want to thank my parents, my mom, my grandfather, my father, and everyone, and my friend. So yeah. So we will so the kernel of this group homomorphism is actually this only, SL2Z mod PZ, and it's isomorphic to PZ, Z mod PZ, a multiplicative group. Now the cardinality of this group is actually p minus 1, because we won't take the 0th element in the multiplicative group, and then we are done, showing that the index of this group SL2Z mod PZ in GL2Z mod PZ is actually turn out to be p minus 1 with this homomorphism relation. And rest part is trivial, showing that the order of this subgroup is just nothing. Order of this is actually nothing to do with more general things. Yeah. And so next we are going to, I think that the video is already too long. I just stop it here to observe the time. Sorry for that confusion about the part of saying the order of the SL2Z. In the LaTeX note here, I actually mistakenly wrote N instead of P, But these are the results that we actually quote from this good question. So I just point out the results separately. So these are the two results that we actually got. And following the book, there is an exercise that shows that we can actually get even further, that for some power of p, where p is a prime number, p to the n, then we can actually get this relation. And the approach is actually same that we actually did in this part. So I think I don't need to do it again. You can just follow the book if you need the proof of this part only. Follow the book. Yeah. Now the main topic of this video of lecture 2 is that to actually solve, or you can say understand, this question, a beautiful question which actually states the relation. I actually defined the index of the gamma n. So earlier I said that the index of the principal congruent subgroup gamma n is finite. So earlier we actually shows that, yeah, the index is finite. Now actually we are actually getting the exact index by this formula. So that's why this question is beautiful. And even if when you solve it, so I'll just show the glimpse of the LaTeX part in two parts. So the video might get a bit longer, but I will prove it with patience. I won't rush because I like this question very much. So let n be natural number, and by unique factorization we can actually write it in terms of some p, where pk's are primes, alpha k and alpha k are positive, or you can say the non-negative integers, and pi's are distinct primes. Yeah. Primes. Yeah. So now again there is an index, right? And actually you can try it like thinking of again a group homomorphism or a normal subgroup. That's how I thought. It's not so natural, but it just, you keep on trying different approaches and then you just hit up with a good example, or you with a good approach. So don't think that I was just able to grasp everything at once. Sometimes I just struggle, sometimes I see the solution, and sometimes the answer hits. And that's so we actually want to construct a group homomorphism, say psi, from SL to Z to SL to Z mod NZ. Yeah. And the map is defined to be we taking A to A mod N. Okay, so the modulo N. So the map is actually well defined, you can check it, and it's even a surjective map. So I guess we actually defined this map to be surjective also previously. Now easy observation is that you can just write in a one line and you will get the result. What I'm going to state right now is that the kernel of this group homomorphism kernel of psi is actually the principal congruent subgroup modulo gamma n. Yeah. So that implies combinedly as SL to Z quotient or mod by, or I just better write in this way, gamma n congruent to, not congruent, sorry, isomorphic to SL to Z mod NZ. So just because the kernel is gamma n. Yeah. Now everything is clear up to this far. We actually saw this result earlier also, and we actually concluded that the with this part to be finite, the index of the gamma n in SL2Z is finite. The next step is that we want to make it more good looking, something which is isomorphic to this group, and eventually if it's isomorphic to this group, then it will be isomorphic to this group, and we want a form of this group whose order is easy to calculate. So recall from ring theory. So for n described over here, so we are actually going to state for that n, z mod nz, and I'm sorry that if I might sound louder sometimes, I just got excited. Hope your ears won't hurt. And this can be isomorphic to, it is isomorphic to z of p1 alpha 1 z cross z over p2 alpha 2 z and dot cross z z mod pk alpha k z. Yeah. So using this part is actually using Chinese theorem. Now we actually move further, and because this theorem is actually true for rings, so it should be true for groups also. And if you able to recall that we actually stated in the first lecture that the SL2Z is a group when R is a commutative ring, and it's the commutative ring already, so we can actually define all these things and just separate what I'm going to write next. All that thing makes sense. Is isomorphic to SL2Z, z by p1 alpha 1 z dot SL2Z pk alpha k z. Yeah. So I just separated all these parts from over here and put the SL2Z on it. Now it's now easy. See, so we were actually aiming to find a good group which is isomorphic to this, whose order is easy to calculate, and over here we are actually able to construct a isomorphic group which is this, and whose order is actually easy to calculate. Using the Chinese remainder theorem, we get this relation, and why it's easy to calculate the order of this group is because of using this result. Again, I just showed for n is equal to 1 over here, but I gave it as an exercise for p to the power n for general n. It's not that difficult, it's actually constructive. You should just follow the book for that, and if you are able to prove on your own, then it's much good for you. Yeah. So now we are actually very close to prove this theorem, or just you can say the problem. Now now from combining these two, we can state SL2Z gamma n isomorphic to this good looking group. It's actually good looking because we are actually kind of factorize, not actually the factorization, but kind looks like the factorization. Yeah. And the index of this, so this group gamma n index is actually equal to the cardinality of this group, or the number of cosets you can say. And this cardinality is actually equal to the cardinality of this group. So all we just need to do is that to find the cardinality of SL2Z, or you can say P1 alpha 1 Z SL2Z, sorry, P1 PK alpha K Z. So all we need to do is to find the cardinality of this structure, and we showed earlier that the cardinality, actually we wasn't able to show, but we were actually make our note or the result of finding the cardinality of such group, and it's actually equal to Pi alpha it's actually equal to Pi 3 alpha I minus 2 Pi square, for general I ranging over 1 to k. Yeah, the cardinality looks like this: minus 1, and just taking out the factors we actually get what we actually wanted to, and rest part is just the product of, you can say, run over all the factors who divides n, all prime factors who divides n. So we actually able to find the relation. So this contribute for n cube, and this contribute to the product over p divides n. And now we are done. The proof is done. It's kind of a long proof, but it's an interesting, and I like that proof so much. And this video is already pretty long. I will just stop it over here. I was thinking to cover up to few more topics, but because this video is long, I will make the next video a shorter length. Yeah, thanks for watching, and if I did some mistakes, sorry for my bad handwriting. It's not that bad in real life, but actually I'm not used to iPad, so yeah, that's why. So thank you for watching. If you get confused in any step, I just make a comment, then I will get back to you. I will also mention my email, so I just write my email just in case if you get any doubt, and if I'm not able to respond in the comments, because I don't know if someone gets doubt after a year or so. So it's actually, the email ID is this: adashkumar130831@gmail.com. Yeah, you can just send me your doubt if I'm not able to reply to your comment in 1 or 2 days. Yeah, thanks for watching. Thank you. Yeah, hope it's helpful.